The single thing that scares people away from statistics is the formulas. They picture a thick textbook, a wall of Greek symbols, dozens of named tests to memorize, and they quietly give up. So here is the truth, said plainly. Statistics is not a pile of formulas. It is one idea, repeated. You never get to see the whole world. You only ever get a noisy glimpse of it. And statistics is the honest art of reasoning from that glimpse, saying what it really tells you and how sure you are allowed to be. And almost everything fits on a single picture, which we will reuse the whole way through. On the left is a population. Every customer, every voter, every measurement, far too big to ever see in full. So you reach in and pull out a sample, just a handful of points. From that handful you make an estimate, and you carry an honest measure of your own doubt about it. Distributions, sampling, confidence, testing. Every chapter in this video is just one more thing happening on this exact picture. Watch it grow. Chapter 1. Statistics is reasoning under uncertainty. Start with the wall you can never cross. The full population is out of reach. You simply cannot weigh every person or poll every voter. And the thing you actually want lies behind that wall. The population's true average, which statisticians write with the Greek letter mu. See that dashed violet line? That is mu, the real answer. And in real life, you never get to see exactly where it sits. Every honest method in statistics begins by admitting that you're working from incomplete information. So what do? You draw a sample, those lit up dots, and you take their average. That sample average, written x bar, is your best guess at the hidden mu. Now look carefully at the picture. The solid line, your estimate, lands near the true mean, but not exactly on it. There is a gap. And that gap between what you measured and what is really true is the entire game of statistics. Everything left in this video is just a careful way of measuring that gap. Chapter 2. Distributions describe the world. Before you can reason about uncertainty, you have to describe it. And the tool is a distribution. A distribution is not a single number. It is the whole shape of the possibilities, which values are common and which are rare. Two numbers pin that shape down. The first is the mean, the center, the balance point. See the marker where the values balance. The second is the spread. The variance, or its square root, the standard deviation, shown by that band. Low spread means tight and predictable. High spread means wild and scattered. And one shape shows up again and again, the bell. Heights, measurement errors, the noise in a sensor, test scores across a city. Astonishingly many things pile up near a central average and thin out smoothly on both sides. This is the normal distribution. It has a lovely rule of thumb. About 68% of the data falls within one standard deviation of the mean, and almost all of it within 3. Remember this curve. In the next chapter, it shows up where you would least expect it. Chapter 3. Sampling and the central limit theorem. Here is the most magical fact in all of statistics. Take a sample, average it, and drop that one average into the panel below. Now take another sample, average it, drop it in, again and again. Watch the sample averages pile up into a histogram. And here is the miracle. They settle into a bell. A clean, normal curve built entirely out of your repeated guesses. This is the central limit theorem, and it is the sturdy bridge that carries you from a little bit of data to genuine confidence. And the part that feels like cheating is this. The shape of the original population barely matters. Pour in something skewed, something flat and uniform, even something with 2 humps. And as you average enough draws, the means go normal anyway. Any shape in, a bell out. That is why a poll of just a few thousand people can speak, reliably, for a country of millions. You are not studying the messy population directly. You are studying the tidy, predictable distribution of its averages. But confidence has a price, and it is worth knowing exactly. The spread of those sample averages has a name, the standard error, and it equals the population standard deviation, sigma, divided by the square root of the sample size, n. The key word is square root. Watch the bell narrow as the sample grows. Because of that square root, to cut your uncertainty in half, you do not need twice the data. You need 4 times as much. It is the law of diminishing returns, made exact. Chapter 4. Confidence intervals. So you should almost never report a single number. A lonely point estimate hides all of your doubt. Instead, wrap a range around it. Take your estimate and go out by roughly 2 standard errors on each side. That green bracket on the picture is a 95% confidence interval. It says, out loud, both your best guess and how uncertain it is. Honest reporting is not the answer, is 42. It is the answer is 42. Give or take 3. The width of the bracket is the width of your humility. And let us be precise about what 95% confident really means, because nearly everyone gets it slightly wrong. The interval is your estimate plus or minus about 1.96 standard errors. But here is the subtle part. It does not mean there is a 95% chance the truth lies inside this one particular bracket. It means the method itself is reliable. If you repeated the whole study many times, 95% of the brackets you built would capture the true value. You trust the procedure, not any single interval. Chapter 5. Hypothesis testing and p-values. Now, how do you decide whether an effect is real or just noise? The logic is delightfully backwards. You start by assuming the boring story, that nothing is going on. The coin is fair. The new drug does nothing. We call that the null hypothesis. Then you ask a single question. If that boring story were true, how surprising is the data I actually saw? If your result would be a genuine shock under nothing is going on, then maybe something is going on after all. You argue by defending the dull explanation and watching it fail. And that surprise has a number, the p-value. Picture the world where the null is true. A bell of all the results you would expect from pure chance. Now mark where your data actually landed. The p-value is the size of that shaded tail. The probability of getting a result at least this extreme, if nothing were really going on. A tiny p-value means your data would be astonishing under the boring story. So you start to doubt the boring story. That, and only that, is what a p-value measures. And because it is so easy to misread, let's nail down what a p-value is not. It is not the probability that the null hypothesis is true. It assumes the null and measures the data's surprise, not the hypothesis's truth. A p-value of 5% does not mean a 95% chance of a real effect. And it says nothing about how big that effect is. And a result that is not statistically significant does not prove there is no effect. Absence of evidence is not evidence of absence. You may just lack the data. Chapter 6. Correlation, causation, and the classic traps. One last warning, and it may be the most important sentence in this whole video. Correlation is not causation. Watch these two lines climb together. Ice cream sales and drownings, rising and falling in near perfect step. It is tempting to say cons are dangerous, but they are not. Both are quietly driven by a third thing, the summer heat. Two things moving in lockstep might share a hidden common cause or be sheer coincidence. The single deadliest mistake in all of data science is mistaking a pattern for a reason. Stay suspicious. And there are classic traps that can flip your answer completely. The first is Simpson's paradox. A trend that holds in every single subgroup can reverse the moment you pool everyone together. A treatment that wins in each group can appear to lose overall, just from how the groups are mixed. The second is selection bias. If your sample is not really the population you think, only survivors, only responders, only the people who showed up, then your tidy glimpse quietly lies about the whole. Always ask who or what is missing from the data. So let's hold the entire field in one breath, on the one picture we have been building. A population you cannot see. A sample you can. A distribution of estimates that the central limit theorem hands you for free. And an honest bracket of doubt around your answer. Distributions describe the world. Sampling connects your little glimpse to the whole. Confidence intervals and p-values put a number on your uncertainty, and you stay suspicious of every pattern. That is statistics. Not a pile of formulas, but reasoning under uncertainty. If this finally made statistics click for you, if it stopped being formulas and started being one clear way of thinking, there is a whole series like it on machine learning, deep learning, and the ideas behind modern AI. Keep that curiosity burning. Subscribe for more such intuitive videos.